Bismillahirrahmanirrahim. Wireless channel impairments. The first impairment is noise. You cannot get rid of noise. Noise is everywhere because it is actually the thermal noise that is everywhere. What is noise? Noise is any unwanted signal. Any unwanted signal is basically a noise for your system. But there is one noise that is almost inevitable, and that is the thermal noise. Because wherever there are, for example, electronic components, even they will produce some kind of heat. And that heat is basically modeled as additive white Gaussian noise, right? So the next thing is path loss, the loss in the power as the radio signal propagates. This is the path loss. Shadowing, this is due to the presence of obstacles in the radio path. And fading combines the effect of multipath propagations, rapid movement of mobile units, and reflectors. So all of these things contribute to the wireless channel impairments. Regarding the fading, the signal copies follow different paths and they undergo different attenuation, different distortion, different delays, different phase shifts. So the system performance can be severely degraded by the fading. So in this figure, you can see on the y-axis, there is average bit error probability. We're talking about the digital system. So in case of digital system, instead of SNR, we talk about it's a better metric is a bit error probability, BER, right? And on the x-axis, we have the average SNR in dB. So as far as AWG channel is concerned, it considers the thermal noise affecting the signal, while a relay fading channel models the rapid fluctuations of the signal amplitude due to multipath propagation, which is a common scenario in mobile and urban communication. And therefore, we usually talk about AWGN for the noise and AWGN and relay fading, which is the non-line of sight kind of fading whenever we're talking about a communication system. So you can see that in case of AWGN channel only, so we have the average bit error probability having a sharp dip as you increase the corresponding SNR, the corresponding average bit error probability is getting reduced like this. But if there is relay fading, the challenge is more, and therefore it's not a sharp fall in the bit error probability. Rather, it's sort of a linear downward trends you can see. Very important parameters of fading channel that you need to remember. The first one is the multipath spread. Very important. It tells us the maximum delay between the path of significant power in the channel. I repeat, it tells us about the maximum delay between paths of significant power in the channel. So let me annotate. This is a transmitter. This is a receiver, right? This is a transmitter. This is a receiver, right? We're talking about the multipath spread. So at the receiver, you get a signal, which is this, at time t1. And then you get another signal at, say, time t2. And then you get another signal at time t3. So we suppose that all of these three signals cross, say, a threshold of some power, right? So the time between t1 and t3 in that case would be the multipath spread, because at time t1, you got the first multipath component. At time t3, you got the last multipath component that had the significant power. So the time difference between t1 and t3, in which you get significant power in the channel, that basically corresponds to multipath spread. So that is basically the multipath spread, and obviously we have Tm showing us the time. So we are talking about the delay. Next is the coherence bandwidth, another very important parameter of a fading channel. It gives us an idea of how far apart in frequency for signals to undergo different degrees of fading. For example, at frequency f1, you get some kind of fading. At f2, you get some kind of fading. At f3, you get some kind of fading, right? So it gives an idea in frequency for signals to undergo different degrees of freedom. So coherence means sort of same, right? So those frequencies, say from f1 to f3, for example, right? So f1 to f3, we get same kind of fading. So we will say that f1 minus f3 mod, that is basically the coherence bandwidth, because this is the frequency range at which you get sort of similar kind of a fading. So as you move away from this del fc, you get some different kind of fading, right? So del f is basically that range of frequency for which you get the same kind of fading. And you say this is the coherence bandwidth, at which the range of frequencies at which you see kind of coherence in the signal. Next is coherence time. It gives a measure of the time duration over which the channel impulse response is essentially invariant or highly correlated. So this is that time at which your channel behaves the same way. So for example, at time t1, your channel behaves in some kind of way, and in time t2 it behaves in some kind of way. So this range of t1 minus t2 would be the coherence time. That again, you can see the word coherence time. So that time duration at which you see the coherence in the channel, at which you see coherence in the channel. So beyond this time, you will see different kind of phenomena. So you can say the impulse response beyond this time would not be coherent, and therefore this is the coherence time, right? Next is the Doppler spread. It gives us the maximum range of Doppler shift, the maximum range of the Doppler shift. So you get some kind of Doppler F1. So for example, FD1, FD2. So that maximum range of Doppler shift in any scenario that will correspond to the Doppler spread. So these are the four different parameters of fading, which are very important. And now, given that you know what these parameters are all about, the next thing is the classification of the fading channels. Very important and very important terminology. This is the frequency selective fading, frequency non-selective fading, fast fading, and slow fading. What is frequency non-selective fading? If the signal bandwidth, the signal in question, is less than del fc, which is del fc the coherence bandwidth. So if the signal in question, that bandwidth, the bandwidth of that signal is less than the coherence bandwidth, we say that the phenomenon of frequency non-selective fading would occur. In case of frequency selective fading, the signal bandwidth is greater than the coherence bandwidth. If the signal bandwidth is greater than the coherence bandwidth, we say a frequency selective fade. Does it make sense? Yes, it does make sense. Why? You say that your signal that is in question has a bandwidth that is greater than the coherence bandwidth. So obviously, if the bandwidth of the signal is greater than the coherence bandwidth, obviously its frequency range lies in that range at which you get some kind of selectivity in the frequency. At different frequency, your signal is going to behave differently, because your signal's bandwidth is greater than the coherence bandwidth, and beyond coherence bandwidth, it's going to behave differently. So that is why you can just figure out the name, frequency selective. So it is dependent upon the frequency. It is dependent upon, this kind of fading is dependent upon the frequency. In this case, you said frequency non-selective, because your signal's bandwidth was within the range of the coherence bandwidth. So since your signal's bandwidth is within the range of coherence bandwidth, it was not going beyond that coherence bandwidth. So obviously, it's like independent of the frequency. So you can relate this thing with the name as well. And then we have fast fading. Again, you can see symbol duration n is less than the coherence time. This is the coherence time, and your symbol duration, whenever you talk about symbol duration, obviously you say you're talking about a digital system and there are some kind of symbols. that correspond to number of bits. The number of bits make a symbol, right? So the symbol duration, the number of bits that are in question, the time duration of those bits is less than the coherence bandwidth, we say that the fast fading would occur. And when the symbol duration is greater than the coherence time, right? When the signal duration is greater than the coherence time, we say that a slow fading would occur. That a slow fading would occur. So this is the example of a fast fading versus slow fading. The line in the middle is showing the slow fading and the multiple fluctuations that are happening over a very small time that corresponds to the fast fading. Now the question, how to mitigate this fading? How to mitigate the issue of fading? So the fading problem can be solved by adding a fade margin at the transmitter. So at the transmitter, you add some kind of fade margin. So this is not a power efficient technique. This is not a power efficient technique. So what can be another solution? Another solution is to take the advantage of the statistical behavior of the channel. Since your system is stochastic in nature, your system is probabilistic in nature, you can take the advantage of the statistical behavior. And what is the meaning of the statistical behavior? You take advantage regarding the time correlation of the channel, regarding the frequency correlation of the channel, or the space correlation of the channel. Right? We're going to see that. What is the basic concept behind that? The basic concept is to transmit the signal via several independent diversity branches to get independent signal replica. I repeat, you transmit the signal via several independent diversity branches. What are those diversity branches and on what basis? We will see that shortly. But you have to transmit the signal via independent diversity branches to get independent signal replicas. You don't get signals that are dependent upon each other. You get independent signal replicas. So in other words, to have diversity, what we need is, the first thing, you need to have multiple branches. You need to have independent fading on all of these branches, and you need to process the branches to reduce the fading probability. So what is the diversity? Since you have talked about diversity, what is the diversity? Diversity schemes provides two or more inputs at the receiver such that the fading phenomena among these inputs are uncorrelated. By uncorrelated, you can say, for the time being, you can say that independent. Diversity means you provide two or more inputs at the receiver said that the fading phenomena among these inputs are uncorrelated. So if one radio path undergoes deep fade at a particular point in time, another independent or at least highly uncorrelated path may have a strong signal at that input. So you say you have two paths. So you say if one path undergoes fading, the other path is independent of that first path. So it's quite possible that it might not have undergone that fading phenomena that the path one has come across. So there's a probability of a deep fade in, by deep fade, it means the signal is lost. Whenever you use the word deep fade, it means fading to such an extent that the signal is beyond or below a certain threshold, not being able to call as a signal. You can say that as a noise. So if the probability of a deep fade in one channel is P, the probability for n channels would be P power n. You know the maximum probability is 1, and the probability is always between 0 and 1. So obviously anything less than 0 raised to power something will get an even smaller number, right? So whenever you say P raised to power n, that is even smaller number than this P. So if you have chances of fading in one path as P, the chances of fading in two paths in that case would be even lesser. For example, you say the probability that your channel will go into deep fade is 0.5, right? So if you have two independent channels, in that case, the probability of going in the fade would be 0.5 power 2. That is an even smaller number. 0.5 power 2 is even a smaller number. So chances of going into the fade has reduced, because you say that if one of the channel is in fade, the other channel, it's not necessary that it has also gone into the fade. So what are the requirements of diversity? First thing, multiple branches. Number two, low correlation between branches. You need to have low correlation. If you have correlation between the branches, then it is possible if one branch goes into the fade, the other branch can also go into the fade as well, if the two branches are related to each other. So you need to have independence to such an extent that they are uncorrelated to maximum extent, right? So if multiple branches are highly uncorrelated, like this, for example, this rho is equal to 0, right? Rho is equal to 0.7 means they are related. 0.99, you can see that the red line and black lines are almost similar. These two are highly correlated, and this one is highly uncorrelated. So if the two branches are highly uncorrelated, only then we have benefit, right? Because if one branch goes into the fade, then the other branch will not be in the fade in that case. So we need to have multiple branches, and also we need to have low correlation between the branches. So what are the techniques that we can employ? The first thing is the antenna diversity, space diversity, horizontal space diversity, vertical space diversity, field component diversity, polarization diversity, angle diversity, frequency, time, and multipart diversity. And similarly, if we study in more detail, orthogonal transmit diversity, space-time diversity, space frequency diversity, space-time frequency diversity, open loop transmit diversity, closed loop transmit diversity, right? So these are the things that you can employ. Then we have diversity combining techniques. One is a switching combining, selection combining, equal gain, maximal ratio combining, right? Before we study that, first of all, let us see what is space diversity. The space correlation properties of the radio channel are used as a means of providing multiple uncorrelated copies of the same signal. So you need to have more hardware for that, because you want to employ diversity in space. So if you want to have diversity in space, you need to have more antennas in that case. So let's see this receiver space diversity. You see, you have a one transmitter, and then you have a receiver having a multiple antennas. You have a receiver having a multiple antenna. So this is basically implying what? This is implying receiver space diversity. So M different antennas are used at a receiver to obtain independent fading channels. You want this channel 0 to be maximum uncorrelated with channel 1, with maximum uncorrelated with channel 3, 4, 5. So you want all of these to be uncorrelated to maximum extent, so that if few of the antennas go into the fade, the one antenna might have captured the signal. So this is known as the space diversity. So in that case, this slide, you see the transmit space diversity. So instead of having multiple antennas on the transmitter, you have multiple different antennas at the transmitter to obtain uncorrelated fading signal at the receiver. So obviously, if multiple copies are transmitted from the transmitter from different antennas, so obviously they will undergo different kind of paths. So if they will go different kind of paths, obviously that is a space diversity, right? So one drawback of this is that the total transmitted power is split among the antennas. So if you have power P, so P1, P2, P3, so the sum of all these would be the power that this transmitter P has basically generated, right? Then we have frequency diversity. You modulate the signal through M different carriers. The separation between the carriers should be at least the coherence bandwidth. This is very important, that the separation between the carriers should be at least the coherence bandwidth. Why? Because within the coherence bandwidth, it is going to behave in the same way. So you need to have a difference of more than the coherence bandwidth in order to get out of that range of frequency beyond which the signal is going to behave differently, because coherence bandwidth is that range of frequency within which you get the same kind of fading. So you need to have a separation of greater than del fc in order to undergo maximum diversity. Different copies undergo independent fading. Only one antenna can be used in that case. You can have multiple antennas, but one antenna would be sufficient. The total transmitted power is split among carriers. Obviously, if you're using F1, F2, F3, so obviously with each frequency, you need to divide the overall frequency. You can see in this figure, this is ST, right? And this is ST. So the difference between two of them in the frequency is del f. So if the difference is not more than del f, if the difference is not more than del f, then it is quite possible that again, as if this, for example, upper signal is going into the fade, this is also going into the fade at the same time. So you need to have a difference of more than the coherence bandwidth. Yes. Next is the time diversity. You transmit the desired signal in m different periods of time. Each symbol is transmitted m time. The interval between the transmission of same signal should be at least the coherence time. So how much should be the difference between the two symbols that are transmitted? The difference should at least be coherence time, because within the coherence time, it was going to behave in the same way. So the difference in the time between the two transmitted symbols should be greater than the coherence time. The different copies undergo independent fading if the time difference between the two transmitted symbols is greater than del TC. The drawback is there is reduction in the efficiency. The effective data rate is less than the real data rate. The effective data rate in that case drops down, which is sort of a drawback in case of time diversity. Next thing is the polarization diversity. So in case of polarization diversity, you have different scattering shifts, and that decorrelates the polarization. The advantage is it's a very compact technique, but disadvantage is that unequal branch powers are there and there is less diversity gain. You can say, for example, you transmit a signal at horizontal polarization, another signal at a vertical polarization, or one signal at a circular polarization. And also there is elliptical polarization. Obviously, that is a very interesting field, polarization. But in terms of polarization, you can again get the diversity. The next thing is the diversity combining techniques.